What did the universe look like in its very first fraction of a second? Not a full second, not even a full heartbeat. A slice of time so short that human language barely has a word for it. And cosmologists will tell you that sliver of time decided almost everything about the universe you are sitting in right now. To understand why, picture 3 puzzles that used to keep physicists up at night. Puzzle 1. Look at the sky in one direction, then look at the exact opposite direction. The leftover heat from the birth of the universe is almost precisely the same temperature in both spots. That should be impossible. Those 2 patches of sky are so far apart that light has not had time to travel between them since the universe began. They should never have been in contact long enough to match this closely. Puzzle 2. Space itself, on the largest scales anyone has ever measured, is flat. Not curved like a ball, not saddle-shaped. Flat, like a sheet of paper stretched all the way to the edge of what telescopes can see. For that flatness to survive billions of years without warping, the early universe had to be tuned to an almost impossible precision. Even a tiny error back then should have snowballed into something we would notice today. Puzzle 3, and this one is almost funny. Leading theories of physics predicted the early universe should be littered with strange, heavy particles called magnetic monopoles. We have never found a single one, not one anywhere. So why does any of this matter to you? Because the answer to these 3 puzzles is also the answer to a much bigger question: why the universe looks the way it does at all, instead of collapsing back on itself or flying apart into nothing. In 1980, a young physicist was wrestling with that 3rd puzzle when he scribbled a few lines in his notebook, underlined them twice, and wrote spectacular realization next to them. His idea is now called inflation, and on paper it sounds almost absurd. For a fraction of a second, the newborn universe expanded so violently that a region smaller than an atom ballooned to the size of a piece of fruit, and kept going. That explosive stretch would flatten out any curve in space, the same way pulling a wrinkled bedsheet tight enough makes it look flat, even if you zoom in close. It would also drag distant patches of sky apart so fast that they had actually been in close contact before the stretching began, which solves the temperature puzzle in one stroke. And it would dilute any leftover monopoles so thin that finding one today would be like finding one specific grain of sand somewhere on the surface of the Earth. One idea, 3 puzzles solved. It is one of the cleanest explanations in modern physics. There is just one problem. Nobody has ever actually seen it happen. Inflation is not something you can point a telescope at directly. So how exactly do you test an idea about something that happened before light itself could travel anywhere? The answer turns out to be written across the entire sky, in a signal so faint it was not even discovered until decades later, and even then, almost by accident. It was discovered in the 1960s by 2 radio astronomers who kept picking up a strange constant hiss in their antenna no matter where they pointed it. They cleaned pigeon droppings out of the equipment, checked every wire, even suspected the pigeons themselves. The hiss never went away. It was not a malfunction. It was the entire sky glowing very faintly in microwaves, the oldest light in existence, a faint afterglow from the moment the universe first became transparent, still washing over Earth right now, from every direction as you watch this. Have you ever wondered what the universe actually looked like as a baby? This is it. Faint, static, and almost perfectly uniform. The universe's baby picture. Almost uniform, not perfectly. And that tiny imperfection is the whole reason any of this works. Did you know that hidden inside those ripples of ancient light is a complete record of how fast the universe expanded in the first moment of its existence? Scattered across that ancient light are tiny variations in temperature between one patch of sky and the patch right next to it. We are talking about differences smaller than a few hundred thousandths of a single degree. Measuring something that small means cooling detectors down to a fraction of a degree above absolute zero, colder than empty space itself, just so a single stray photon from 13 billion years ago does not get lost in the noise. To put it in perspective, it is like standing outside on a freezing night and reliably detecting the warmth of a single lit match from a mile away, across the entire sky at once. Those ripples are not random noise. Their exact pattern, how big they are, how they vary from one size of patch to another, is a direct fingerprint of whatever violent process shaped the universe in its first fraction of a second. If inflation really happened the way physicists think it did, it should have left behind two very specific numbers hidden in that fingerprint. The first number describes how the size of those ripples changes as you look at bigger and bigger patches of sky. The second is a trace of gravitational waves, ripples in space itself, that inflation should have shaken loose in its first instant, and that nobody has ever directly detected. Think of gravitational waves as literal ripples moving through the fabric of space, stretching and squeezing everything they pass through, including, in theory, you right now, by an amount too small to ever feel. For more than 40 years, different research groups have raced to pin down both of those numbers as precisely as they possibly can, because the exact values are what separate one theory of inflation from a dozen rival theories. Have you ever stopped to think that the reason we can even debate any of this is because of a photograph of light that is older than every single star in the night sky? That faint light is not just old, it is a message, and every ripple in it is a clue about a process so extreme it makes anything humans have ever built look sleepy by comparison. If stories like this, a genuine scientific mystery slowly getting cornered by real evidence, are the kind of thing you find yourself curious about, hit subscribe. We chase down a new one every week. Now, back to the question nobody had actually pinned down with confidence until very recently. Here's the strange part. Physicists do not actually agree on what inflation looked like mechanically. There are dozens of competing recipes, and most of them fit the basic story just fine. Two of the most popular recipes take wildly different approaches. One tweaks Einstein's own equations of gravity ever so slightly, letting gravity itself power the expansion. The other recycles the particle that gives all other particles their mass, turning it into the engine of cosmic inflation instead. For decades, both of those recipes looked equally good on paper. The only way to actually tell them apart was to measure those two hidden numbers with more precision than anyone had ever managed before. So here is exactly what a fresh look at the sky just found. A group of researchers pooled together data from 4 of the most sensitive instruments ever pointed at the sky, a satellite and 3 ground-based telescopes built specifically to catch this ancient, whisper-faint signal. Think of it like 4 separate witnesses to the same event, each one looking from a slightly different angle, each one catching details the others might have missed. Combining them all gave the sharpest reading yet of that cosmic fingerprint. And on their own, the numbers came back close to what the 2 most established recipes predicted. But what happens when you add one more ingredient? A brand new map of millions of galaxies scattered across the observable universe to that same ancient fingerprint. That is when the numbers moved. Adding that galaxy map nudged one of the 2 key numbers upward, just slightly, not a dramatic swing, barely a hair's width in relative terms. But at the level of precision these instruments can reach, even a hair's width is enough to matter. That small nudge was enough to put real distance between the data and the prediction of the tweaked gravity recipe, the one that had been a favorite among physicists for years. The mass recycling recipe took a smaller, but still real, hit too. Meanwhile, simpler recipes, ones that describe the early universe rolling down a plain, uncomplicated slope of energy, suddenly fit the data noticeably better. Here is the one honest caveat, because this is where real science earns its credibility instead of just chasing a headline. That shift only shows up once the galaxy map is added, and it comes from a mild, still unexplained disagreement between what the ancient light says and what the galaxy map says about how matter is spread through the universe. That disagreement is real, but it is not yet large enough to call it a discovery. It could fade away completely as more data comes in. The researchers behind this describe it as a snapshot of where the evidence stood at the end of 2025, not a final verdict. It is worth sitting with what is actually at stake here. Every one of these competing recipes makes a different prediction about whether inflation happened just once, in one violent instant, or whether, somewhere far beyond what any telescope will ever see, it might still be happening right now. New instruments are already being built specifically to shrink the uncertainty on both of these numbers by more than an order of magnitude within the next 10 years. When that happens, one of these competing recipes for the birth of the universe will finally be confirmed outright, or ruled out for good. We may finally know exactly what happened in that first unimaginable fraction of a second. For now, the universe's own birth certificate just got a little sharper, and one of cosmology's longest-standing favorite explanations has some serious new competition.